Welcome to the deep dive. Today we're putting on our high-performance computing hats. We're going deep into the technical blueprint of some really elite AI video generation.
Really are.
Specifically, we're dissecting the documentation, the GitHub repository, really, for a powerful extension called ComfyUI-LTXVideo.
Yeah, and it's more than just an extension. The source material, it's almost like a technical spec sheet. LTX2 is already a huge name in video generation.
One of the most respected, yeah.
Exactly. And these custom nodes, they basically unlock its professional-grade, high-fidelity features.
So that's our mission today. We want to unpack the reality of working on that cutting edge. What does it actually take, practically?
In terms of hardware storage.
Right. And the specialized model architecture. What do you need to move beyond just simple AI clips and start producing something that's truly controllable, high fidelity, almost cinematic?
Precisely. And we have to look closely at what the developers are asking for, because the prerequisites here, they tell a story about the model's complexity. When you're aiming for the absolute peak of AI video quality, you just leave consumer-grade computing behind.
Let's start with the Getting Started guide. Because, a little ironically, the initial setup is designed to be pretty user-friendly. It's a hallmark of the whole ComfyUI ecosystem.
It is.
The whole point of this ComfyUI-LTXVideo repository is to give you the custom nodes and workflows you need to really max out the LTX2 model's best features.
And the documentation is excellent there. It guides you right past that initial friction point. They use the Comfy Manager, which is, the system's preferred way to handle any add-ons.
Right. So from anyone who's used ComfyUI, this part is incredibly simple. You open the app, you click the Manager button or Strial plus M-Select, install custom nodes, search for LTXVideo, and just click Install.
Restart and you're good to go.
Theoretically, yes, you're ready.
And this is where the documentation drops the first major detail. There's this one phrase: the required models will be downloaded on first use.
It sounds so casual.
It does. But that is the critical pivot point. It's where you go from a simple software install to a serious hardware constraint. That easy install is the lure.
And the hardware demands are the real gatekeepers. That's a perfect way to put it. So let's pivot right to those technical requirements, the things that actually define the system as high fidelity. We're talking about the minimum specs, the hardware that can actually process these enormous models.
So the first absolutely non-negotiable thing is a CUDA-compatible GPU. That's pretty standard for any serious AI work.
Sure.
But the real barrier is the memory. The documentation specifies 32 gigabytes of VRAM or more.
32 gigabytes of dedicated video memory. I mean, if you put that into perspective for the listener, the absolute highest-end gaming cards, they usually top out at, 16 gigs? Maybe 24.
Exactly. This requirement pushes you directly into professional or, data center-grade hardware. It's a different league.
What does that signal about the model itself?
It signals the sheer size of LTX2's latent space, the number of parameters it's handling all at once. With video, unlike a single image, the GPU has to manage not just the spatial detail of one frame,
but the temporal coherence across a whole sequence of them.
Right, and that multiplication of data just explodes. It hits the ceiling so fast, which makes 32 gigs a necessity, not a luxury.
And it's not just VRAM, the fast memory. The system also demands a huge amount of permanent storage. We're talking 100 gigabytes or more of free disk space.
Yeah, just for the models and the cache.
100 gigabytes of models just to start.
And that should immediately tell you you're dealing with a multi-layered, multi-component architectural stack. It's not just one file you download.
Right.
The investment is clearly in hardware and storage, so the payoff, the quality you get, is expected to be exponential.
Okay, so let's assume someone has made that investment, or at least they're curious about what this kind of hardware lets you do. Let's look at the utility. What can you build with these custom nodes?
This is where the example workflows come in.
Yes, the repository includes these clear templates, and this is where the power becomes visible.
And having those pre-built workflows is just invaluable. ComfyUI is a node-based environment, which can look, a little daunting.
For sure.
The examples show you exactly how all the complex components, the upscalers, the different LoRAs, the checkpoints, how they're meant to be chained together for specific results.
And the examples cover the fundamentals. You've got text to video and image to video, but for both of those, they offer a choice.
A full model option, and then a distilled model fast option.
What's the thinking there?
This distinction is a key optimization strategy in modern AI. A full model is, it's maximizing detail and fidelity. It's using the model's entire set of parameters.
Which takes time and all 32 gigs of that VRAM.
Exactly. But the distilled model is essentially a smaller, faster version. It's been trained to mimic the outputs of the big one.
So you sacrifice a little bit of nuance.
A small degree of accuracy or nuance, for a huge jump in speed. It's a difference between a high-res, multi-hour render and a faster but still very high-quality, minute long one. It's a crucial trade-off.
The examples also show it's not just about pure generation. There's a video-to-video detailer workflow.
Right, which suggests that post-generation refinement, adding specific visual textures, that's a core capability here. It's not an afterthought.
But this next one is where the really sophisticated control comes in.
The IC-LoRA distilled model workflow.
Yeah, this one template combines 3 specific controls at the same time: depth, human pose, and edges.
That's fascinating. You're not just making a moving picture. You're making a moving picture where the human subject holds a specific, consistent pose.
And the scene respects real, 3-dimensional depth relationships. It doesn't look flat.
Yeah. If we connect this to the bigger picture, the goal is controlling the narrative and the visual physics, including pose, depth, and edge controls, confirms this system is engineered for high-level continuity and realism.
The very things AI video often struggles with.
Exactly. And all of that control is achieved through this massive library of required models we need to dive into next.
And this is where that 100-gigabyte storage requirement suddenly makes perfect sense.
Yes.
LTX2 with these nodes isn't running off one file. It's a whole ecosystem of specialized components, and each one needs to be installed in a very specific place.
The file management is crucial. Let's start with the core LTX2 model checkpoints.
Yeah.
They have to live in the model checkpoints folder.
And there are 4 options, which kind of mirrors that speed versus fidelity choice we just talked about.
Exactly. You have the dev versions, which likely means development or detail, and the distilled versions for speed. And then they also specify FP8 and non-FP8 versions.
FP8? What is that?
It stands for 8-bit floating point precision. It's a technical way of saying it's a highly compressed version of the model. It runs much faster, uses less memory, but you lose a tiny bit of precision compared to the standard models.
So you choose your core checkpoint based on whether you need max speed or ultimate visual quality.
That's the choice. Then, once you have your core model, the docs require dedicated upscalers for what they call 2-stage pipelines.
And these go into a different folder, model sleetened upscale models.
Right. And they're split into 2 very distinct models: a spatial upscaler and a temporal upscaler.
This sounds important for video fidelity.
It is. It's a crucial detail. In image generation, you only worry about spatial upscaling, making the image bigger and sharper within that one frame.
But with video, you also have to worry about temporal upscaling. What's the difference in what they do?
Well, the spatial upscaler refines pixel details. It resolves blurriness, adds texture frame by frame. But the temporal upscaler has a different job. Its job is to ensure continuity between the frames. It prevents that common AI artifact where textures, like boil or flicker.
That visual jitter you see sometimes.
Exactly. By splitting these tasks into 2 dedicated models, the system ensures you get both high resolution and smooth, stable motion. It's a really smart bit of engineering.
It really is. It shows they're tackling the fundamental continuity problems of AI video head on.
And that level of precision even extends to how the model understands your text prompts. There's a highly specialized text encoding requirement.
The Gemma text encoder.
Yes. You need all the files from that repository, and you have to put them in this very deep subfolder. Model text encoders Gemma 312B ITCAT Q40 unquantized.
So why does a visual model need a big language model encoder like Gemma, and why one with such a long specific name?
Because text to video requires a deep understanding of the prompt. It's not enough to just see keywords like dog or running.
You need nuance.
You need nuance. You need the model to understand, say, a dog running lazily through a misty morning field. Integrating a state-of-the-art LLM encoder like Gemma ensures the system gets those complex relationships, the descriptive adjectives, the context.
So the quality of language processing directly impacts the visual fidelity.
Absolutely.
Yeah.
Especially when you're trying to generate something cinematic.
That makes perfect sense. But the real joy here, the real granular control, it comes from the dozens of specialized LoRAs, low-rank adaptations.
These are the fine-tuning tools.
And they have their own folder, models LoRAs.
Right. You start with a core distilled LoRa, which probably optimizes the faster workflows. But then you get into the image control LoRAs.
These are the visual consistency files we mentioned. Things like canny control, depth control, detailer, and pose control.
So if you need a character to stand exactly centered, you load the pose control. You need clean architectural lines, you load the canny control.
They're like plugins for consistency.
Exactly. It's a surgical approach to correction and refinement. And you don't have to retrain the whole LTX2 model to do it.
But for me, the most exciting part of this entire blueprint, it has to be the camera control LoRAs. This is where the technical documents start to read like a director's checklist.
It's highly technical, but it's purely cinematic.
Right.
They have dedicated control files for specific camera movements.
We're talking dedicated LoRAs for Dolly-In, Dolly-Left, Dolly-Out, and Dolly-Right.
And a dolly move, that's where the camera physically moves towards or away from the subject. It changes the perspective, the parallax.
It's not just a zoom.
Not at all.
Yeah.
And the fact they engineered a dedicated LoRa for this complex perspective shift means you can specify not just what's in the scene, but how the audience experiences it.
And they don't stop there. They also have jib down and jib up.
Which are crane movements, lifting or lowering the camera for those sweeping vertical shots. And then there's a basic static camera control too.
This moves the system definitively beyond simple video generation. This is automated, sophisticated cinematic direction.
It shows the architecture isn't just focused on photorealism. It's focused on storytelling through movement. But that level of control...
It's precisely why the VRAM requirements are so punishing.
Exactly. All these components have to be accessible to the GPU at the same time.
Which leads us perfectly into our last section, optimization.
Mm-hmm.
Even with a 32 gig GPU, which is a massive investment, the developers know that these complex pipelines, with all the LoRAs and encoders loaded, will tax the system. So how do they suggest you manage those resources?
This is where we get into smart resource management. The documentation points to specialized model loader nodes from a file called loadramloaders.py.
The file name alone tells you what it does.
It tells you everything. It's for squeezing performance out of tight situations. These nodes, they manage something called model offloading.
Okay, what is that?
Think of your VRAM as a very small, incredibly fast workbench. A complex workflow might need 20 specialized tools, but the bench can only hold 5 at once. Model offloading is the process of intelligently shuffling the tools, the models and LoRAs, that aren't needed right this second off the workbench and into slower system memory or onto the disk.
So instead of trying to hold the entire 100 gigabyte stack in VRAM and just crashing,
Right.
the process stages the components. The generation can continue, maybe a bit slower because of the shuffling, but it doesn't fail.
Exactly. It's a critical technique for maximizing a high-end system where the task demand still exceeds the available memory. It prioritizes finishing the job over raw speed in those really dense workflows.
And there's also a simple command line tweak to manage memory defensively.
Yes, the standard ComfyUI parameter reserve RAM. If you run a command, say Python -sm main reserve RAM 5, you're telling the system to always keep 5 gigabytes of VRAM free.
For the operating system and other essential tasks.
Exactly. It stops the generative process from grabbing 100% of the VRAM, which often leads to system instability and crashes. It's a defensive strategy to make sure your marathon video generations don't fall apart halfway through.
Okay, let's synthesize all this. What's the fundamental takeaway from dissecting this blueprint for LTX2?
I think if we connect it all to the bigger picture, the knowledge we've gained is that this level of video fidelity, it isn't achieved through brute force. It's achieved through a highly specialized architecture.
It requires the specialized hardware, that 32 gig GPU.
Of course. But just as important is the heavy investment in the software architecture. Dozens of dedicated models, the spatial and temporal upscalers, that nuanced Gemma text encoder, and all those specialized LoRAs.
The complexity of the installation is a direct reflection of the depth of creative control you get.
It is.
So you now understand the architectural depth of this top-tier system and why it's structured this way, even if that 32 gig VRAM is, aspirational for now. It's a fascinating look under the hood.
Indeed. The system is designed to let a technical user craft almost every conceivable detail of the output, moving way beyond basic prompting and into the territory of high-level cinematic direction.
And that cinematic precision, that's the lingering thought here for me. The source material details all these specialized LoRAs, especially those camera controls, dolly, jib, static. If you can engineer highly specific cinematic movements and visual consistency, like depth and pose, into distinct loadable files, what does that imply about the future of traditional camera crews in digital content creation?
That's the question.
I mean, if we can distill the language of cinema down to a set of computational controls, what element of directing or cinematography can't eventually be captured in a control LoRa?
That is the critical question. If the technical components of visual language are already digitized, where does the human creative boundary remain? It's something worth mulling over.
We'll see you in the next deep dive.